Today I wanted to bring a object in equilibrium type of problem. This one in particular is going to require us the understanding of support reactions. And keep in mind that this is a little bit easier because we're still in the 2D types of problems. So this is a really nice step towards working the harder 3D problems that we'll see later. I'll post a video on that as well. So I chose this one in particular because it has some interesting things going on. So let's just get to it. The problem says, determine the reactions on the bent rod, which is, I believe, this copper rod here in the center, which is supported by a smooth surface at B. And by smooth, understand that there's no friction. And by a collar at A, which is fixed to the rod and is free to slide over the fixed inclined rod. So by a collar at A, which is fixed to the rod and is free to slide over the fixed inclined rod. Okay, so that basically means that at A, this can go, it's free to go up and down, but it will resist some sort of motion in other directions, and we'll take a look at that. So before we even get started, the first thing that we should be doing is a free body diagram. So my attempt to do a free body diagram is the easiest possible way. We got that force there, 100 pounds. Then we also got a couple moment clockwise. And then what else do we have? Now the only thing we're missing are the reactions. And this, I guess, is the hardest part, is understanding the reactions. So starting from A, I said that this rod is free to move up and down, right? And when they say that, the kind of concept you should keep in mind is that because it's free to move up and down, and this is a statics problem, there shouldn't be any force or anything making it move up and down. Otherwise, it's not static anymore. It would be moving, right? So it defeats the whole purpose. So the key here is understanding that, and understanding that just because it's free to move in that sense, it does have some sort of support elsewhere. Otherwise, it still move, right? So which way is this being supported? And the way that I would choose to perhaps draw this, I'd still keep the traditional way, which is just simply drawing a x and y component to that reaction. So I'll call this maybe what, RAY, and I'll call this RAX, right? Which we can actually simplify later if we wanted to, and I might end up doing that. I'll get to that in a second. And then we have to think what other supports besides those forces are exerted at A, right? So since this is a rigid body here, this support rod here is a rigid body, it should prevent rotation as well, right? And but not in all directions. It's going to prevent in one direction, and that direction that it's going to prevent it's basically going to be, if we consider this to be the XY plane, it's going to prevent rotation about the Z, because the Z is coming out of the paper. So it's this rod here, due to its geometry, it's not going to allow the object to rotate about the Z. So rotating about the Z means, this kind of rotation, right? It can't physically rotate just because of the geometry, right? However, it can very well rotate about this axis here, but we're not going to worry too much about that, okay? And I believe that's it. So since we're dealing with a 2D problem, that should be the only moment that we're going to be worrying about. We're not going to be accounting for a moment about the X or the Y. And that's it. So let's just include that guy. So we'll call this perhaps, MA, and the direction is a total guess, right? The sign will tell us later. And then that's it. For reactions at A, those are the three main ones we get. Okay. Now the last point of contact is point B, which is right here. I should probably label these guys A and B. And in that case, because that's just a surface contact, the only kind of support we would get is a force, right? There's nothing preventing rotation. So the only force that actually exists, and again, I should probably draw this the convenient way, and that's not how I'm gonna keep it. Let me call this RBY and RBX, right? So this contact here should have a reaction in the X direction and a reaction in the Y direction, right? It turns out though that at point B and as well as A, right, the limitations of the geometry also tell us which direction a resultant of these reactions are. So keep in mind, these are just components of one reaction. So these two are components of what we call RA, and these two are components of what we call RB. So we should take advantage of that, especially because we, as a 2D problem, we only have 3 equations to work with. And right now, the way we have it, we have 5 reactions. So we don't have enough equations to work with. So we should do, let me do, maybe now that I talked about it, I'll probably erase it, right? So the whole idea here is that we could still think of it as separate reactions. However, we have to quickly realize that due to the geometry constraints, we're already told which direction the reaction goes. It's not gonna have an X. Well, we will have an X component and a Y component, but it's already telling us the direction of reaction A. So we don't have to split it into X and Y components to then find out which direction it's really going. I hope that made sense. Kind of went a little bit out of my way to explain you that. A lot of people just jump into it, but I figured it'd be very useful to actually know where this is coming from and why we sometimes split them into X and Y components. So in this case, remember we did have that bar here. So the reaction is going to go perpendicular to that contact point at that bar. Okay, so that's how we're going to know. And the same thing here, we did have that surface incline, so the reaction is going to go perpendicular in that direction. So with the known angle, so here for instance we do have an incline, right? We should be able to figure out that angle. So that angle should be, let me see here. So tangent of 5, inverse tangent of 5 over 13, we get 21.03. Oops, go back here. So that's that angle there. And then this guy is a little bit more complicated. Let's see how we can figure this out. So, okay. So we have that, for instance, let me see. We did have a triangle there. Let me expand it here. And let me draw the triangle right here. So we have a 3, 4, 5, right? This triangle here that I'm talking about, which makes this, let me see it. So this is a line cutting through. It makes this angle here, probably use a highlighter. It makes this angle here equal to this angle here, right? So if you can figure that out, that's also 90 degrees. It's a little bit of, working through it, but we'll get through it. So let's figure out what that yellow angle is first. So that would be, and I believe I actually got the wrong angle there. Well, I'll fix it later. It's not 21. It should be something else. or did I do it right? Yeah, I did it wrong. So I'll fix it. As always, doing this on the fly, right? I don't prepare for these because I want to, show you that it's okay to go through this and, reiterate and evaluate and refresh, right? On those problems. Anyways, so we've got here this triangle, and I'm going to do inverse sine. So that's what I should have done on the other one, not inverse tangent. So 4 over 5, right? So that's 53.13. That's the angle. So 53.13. And this guy here should have been, if I do inverse tangent, that would have been 5 over 12. That's different, right? 22.62. Boom. Okay, so getting this angle here is, a little bit tricky, right? So let's think about that. They're not the same, or they shouldn't be, but maybe they are. Let's see. So this is 90 degrees total. It's 90 degrees total. So the way that I would reason through it is, a quicker way without playing too much with the geometry is, think about as if this red line here was, perhaps, let me see if I can change this color here. Think of this dotted line that I'm, reinforcing here as if it was right here where I'm pointing, right? If we move it to the left, this perpendicular red arrow was right here, and it moved down by this much. So the same amount that this arrow moved down, this also moved. So that amount is 90 minus 53.13. So 90 minus 53.13, that's how you should think about it, right? And you should be able to prove it to yourself with other geometry tricks. This is a little bit easier if you have a perpendicular type of situation like this one. That force is going to move as the other geometry also moves. So that's kind of like how I do it quicker. Anyway, so we figure that out, very important. Now we need to figure this guy out as well, just, because this is perpendicular to it, right? But we need to find out how much of it is with respect to the x-axis, right? Or the y-axis, whichever one you want to play with. And let's see how we can reason through this guy. So perhaps I should draw it here. That would be a little bit more clear. So this angle here was 22.62. And we're trying to figure out, okay, so that's a little bit easier, right? These are just alternate internal angles, right? So this is just a lot easier. So these are the same. Remember how I said that sometimes they're actually the same? In this case, we lucked out. They're the same, right? This angle here is the same as this angle here. So that's super easy for us, right? So we got that going. Now we're ready to solve, right? So the geometry is a little bit of the tricky part on this, and understanding the reactions, right? So here we go. We're still calling this guy RA, and we're still calling this guy RB. Okay? So let's do that. Let's do some. First thing that I want to do is sum of the moments about A. Okay? Equals to 0, statics. We have our MA reaction, which is clockwise, so negative MA. It's coincidence that I ended up labeling it MA and then some of the forces MA. It's coincidence. I could have called it just M or MRA, something like that. It's just coincidence. This means some of the moments about A, right? So I'm taking the moment about this point, okay? Should be equal to 0, statics. And then we have a reaction moment at A, which I ended up calling MA, right? Then we have the moment caused by the 100 pounds, which is negative. So this 100 pounds is going to want to rotate us clockwise, which I defined as negative. So 100 times that distance is 100 times 3, right? We also have the couple moment that was pre-existent. It's also counterclockwise, so minus 200. And then we have the reaction at B, right? The reaction at B is causing a moment at A, right? The easiest way that I can think of doing this is just splitting B into components, right? So if you think about this, let's just say point B was, this point that I'm drawing here, there's going to be a RB, remember previously, right? There's going to be an RBY and an RBX. However, instead of calling them RBY and RBX, we're just going to call them RB cosine something or RB sine something, which is the angle that we figured out, right? So let me just do it here, right? So that would be this guy and this guy. And actually, I should probably draw these according to the geometry that we're given and the way that I predefined them, because otherwise it will be completely wrong. Let me erase some of the craziness that I got going on here. The angle was important. So let me see here how I can make this better for us. Okay, so if I split that guy into components, I'm gonna have one going this way and one going up. These two are gonna cause a moment, right? And why did I drew them that way is because I defined that reaction to be supporting in that direction. And so it's going to have an x component like that, and the y component is like that. It has to be that way, right? I can't do it the other way around for either one. That would be incorrect. So the x component is going to cause, so this, let's just say this is the x component, right? It's going to try, so we can move this force closer to the point of interest just to get an idea. That is totally valid, right? If we move it, it's going to want to rotate us also clockwise. So minus RB. And then in this case, we can do RB. Let me see. What would be easier for us? So if we have this guy here, and the other guy was like that. The way I drew my geometry, that would be a little bit funky. I should have probably figured out some other angle. Let me think about this real quick, guys. Sorry. I apologize. Let me see how I can make this a little bit easier on us. Oops. Oh, it's too much. So, wow. Okay. Why is it coming out like that? I don't know why it's the thickness of the pen so much. Oh, because it selected a marker. That's why. Okay. So what is this angle here? So I make this guy here. It should be... I should probably stick to the angle that I was working with, right? So here we go. I figured it out. So this is also 22.62. Okay, so draw it on the side here. Let me see where I can draw it so it's easier for us. Here we go. So RB is going that way. This would be our RY. And then this would be our RX. RBX, sorry. This is also 22.62. Okay? So, which makes our X component of our reaction be, RB times sine of that angle. So RB sine 22.62. Correct. Awesome. And we're at a distance of 2 feet perpendicular to the point of interest, which is A. So times 2. And I think we're only missing the y component. So the y component is going to want to rotate us. So we can transfer the y component here. Okay. And that is perpendicular to point of interest A, 6 feet away. And it's going to want to rotate us in the positive direction that I defined. So plus RB. And then this time around, we're dealing with cosine 22.62 times the distance of 6 feet. That's how far away perpendicularly we are to A equals 0. Boom. So now we can calculate our reaction B. So we got this by, actually, we have 2 unknowns, so we cannot calculate that, right? We cannot calculate that. Okay, so this is just an equation. Let's keep going. So sum of the forces in the x direction, we cannot calculate that. That's right. We only have two unknowns in one equation. We have to jump to the next one. Okay, so let me see how I can perhaps try to fit all of this into, perhaps if I zoom out a little. There we go. If I zoom out a little, I should probably fit. Yeah, there we go. So let me see if I can move that guy there. So RB. Okay. And then I'll do the other equation there. I'm going to say positive to the right. We have, what? We also have, well, we wouldn't count the moments in this case, right? So the only forces acting that have components acting in the x direction are the reactions, right? So we would have, if I define positive to the right, we have negative RB sine 22.62. That's, this guy right here going in the left direction. Well, that's why I put the negative sign. And for the other one, I had it defined like this. Well, a little bit off here. And this angle was 36.87. This was RA. So it's going to have a y component this way and an x component this way. So that's positive. So plus RA cosine of 36.87. And that's equal to 0. So we can solve one for the other, get that relationship. But before we do that, we need to do some of the forces in the y. Let me see if I can perhaps try to fit everything into one page, and then I'll get us the answers, right? Because I can plug it all in my calculator and get us the answers. So let me move it up a little. Okay, sorry about that. Okay, let me extend this guy. I'll define positive up, and now with all the drawings we have, it's a lot easier. So we got RB cosine of 22 plus RA sine of 36. Oops, what's going on? How did that happen? Some sort of bug. Sorry. Good thing it didn't mess it up too much. 36.87 equals 0. I already wrote it down, so no need to write it down. All right, and that came from looking at this guy up, and then this guy up. Hence why both are positive, right? And that's it. So let me see if I can plug this in my calculator and get the answer for us. So we have a 3x3 system of equations. So bear with me for 1 second. I'm going to put RA first. So 0. So for the first equation, we have 0 RA. And then negative 2 times sine 22.62 plus cosine 22.62 times 6, correct? Yep. And then minus 1 for MA. And everything adds up to, so 200 plus 300. There we go. So first line correct. And then I said RA was first, so cosine of 36.87. I'm building a matrix on my calculator, so bear with me. Negative sine, which by the way is one of the easiest ways to solve those simultaneous equations, if you're allowed in your class. 0 moment equals to 0. And then we have RA sine 36.87. And the other one is cosine 22.62. 0 moment, 0, 0. Solve. Let's see if we get the right answer. So after plugging it all in the calculator on a matrix, 3x3 matrix, I was able to get the answers. And it turns out that the moment support at A is equals to negative 106.35 foot-pounds, which means that, we guessed the wrong direction. That's not a problem. RA turns out to be 39.7 pounds, correct direction. And RB was 82.54, and that's it. It looks correct to me, and that's what I got. Oops, that's the answer. All right, if you guys have any questions, please let me know, and if you like this, stay tuned for more. Okay, thank you so much. Bye bye.